Making a start here on Tuesday the 9th of October. I guess the first item of business is to remind folks about the upcoming exam, which is scheduled for Thursday for local folks at this time and place. Plan to have what we used to call a second seating for people who can't make this session, either local folks who really have some other thing they need to do that's pressing during this time. I hope you won't find anything more pressing than this. Also for, and when I say local folks there, I'm talking about students who are registered in sections 500 undergraduates and 600 graduate students. For students who are local but not live in the classroom with us, the people who are in 599 and 699, I want you to take the exam the same day, that is next Thursday, but it doesn't necessarily obviously need to be at this time. In fact, I've arranged to have a follow-up session right after this period starting at 12:30, and I'd like to have folks who are unable to be in this session at 11:10 to be in that one. The distant people who are really distant, or people in the rare cases who are local but just have to be someplace else that day, need to be working with me to arrange for a proctor. Most folks already have done that who need to, but I still am waiting for a couple. And I guess my concern is people who are in that position are probably not paying close attention and aren't even hearing this message. I'll send out an email after class to remind people. So last time we ended, I think, by talking about simple applications of energy budget analysis to arrive at things like estimating the maintenance requirement of the ration and the rate of weight loss in the case of starved fish. And you should be able to do simple problems like that. It amounts to solving a simple equation for an unknown, and you have to apply some rules of thumb in order to do the solution. And if you were unable to come up with a rule of thumb, but you could arrive at the general symbolic representation of the solution, then that would be worth quite a lot of credit on the exam. But I would prefer that you go ahead and make the proper assumptions having to do with things like what? Like the fact that the energy cost for food processing that we call A sub D is typically about 15% of A sub C. That urinary losses are 5% of A sub C, or for lack of a better guess, 5% of A sub R, whichever is greater. That fecal wastes reflect the digestibility of the feed, and if you're not told any better, I would assume that the digestibility of the feed is probably about 80%. Those kinds of things. That wet biomass of fish and their forage typically has about 1,000 calories of energy per gram as consumed. On the other hand, dry feeds typically have 4,000 or 5,000 calories per gram because they are much drier and have a lot less zero yielding energy of water that yields zero energy. So those are the kinds of things that are what I call rules of thumb that are regularly applied in bioenergetics to do analyses in cases where you are missing some data, actual measurements from the case at hand. And that's frequently the case. So I'd like to move on today and talk about sort of an extension of these ideas of bioenergetics. I won't hold you responsible for the material covered today, but some of what I say today may give you some insights that will help you with some of the stuff that's on the exam, which will be testing over previous material, like the bioenergetics section. I want to talk about the factors affecting energy budgeting, and the first of these is a really important one. It's the size of the animal itself. Little fish do business of all kinds at faster rates, and that's something you already know. The processing of food and the resolution of the materials that are yielded is no exception. Those are also at rate dependent. So you can actually write some of these components of the energy budget, the balanced energy budget, as functions of body weight and the consumption of feed, of course. We've already talked about the part that has to do with feed consumption. Now I'd like to talk about the part that has to do with weight of the animal. Here's the energy budget equation that you've come to know and love. Consumption rate is the sum of respiration, waste, and growth. And the respiration term can be resolved into three components: standard, activity, and food processing, the A sub D term. The A sub R term you can represent as partly a function of weight of the animal that's doing the consuming of the feed, and partly the consumption of the feed itself, the amount consumed. And we've already said that, I've already said right up front when we went through the energy budget term by term, that typically the standard metabolic rate of fish is proportionate to the negative small power, and the size is about 0.2 typically. A lot of debate on scaling of biological processes and ecological processes as a function of animal and plant size, and some folks would rather see a minus 0.25 and talk about the quarter power scaling laws. But I think the bulk of the data come down in favor of a larger exponent, I guess you'd say, something a little less negative, around minus 0.2 instead of minus 0.25. And so standard metabolism then is equal to a coefficient that does the units of the dimensional conversion, S for standard, I guess, multiplied times weight to the negative 0.2 power, we're going to assume, if you're not told otherwise. And we're going to have to leave the A sub A term alone for now, but the A sub D term, we can go ahead and make that conversion to a fraction of A sub C, as we can in the case of A sub W. And you can see here we're taking the nominal assumption, the usual middle of the road assumption, that A sub F is 0.2 A sub C, because we got 0.05, so we get 0.25 total, plus A sub G. And so collecting those two terms that involve fractions of A sub C, we get that 0.4 A sub C here. And I think that's where we got to in our little work through on the energy budget bioenergetics analysis that we did at the end of the last session. We were assuming 0.4. Moving on to the next step of the process, we can rearrange terms here and solve for everything that's not a function of either consumption or weight, just by moving those two terms over to the left. So we get A sub A plus A sub G. In other words, the activity and the growth components, if the budget is going to be balanced, would come down being about 6/10 of A sub C plus, or minus rather, plus a negative term, minus S times weight to the minus 0.2. Now, if we go ahead and define the maximum scope, the maximum sum of A sub A and A sub G as the bioenergetic scope that the animal has, and in this case we need to be careful and go ahead and add that prepositional phrase, for activity and growth. So, bioenergetic scope for activity and growth. Considering those a sum that we can't resolve at this point, although we're going to make some efforts here in a moment. And we have to reason that bioenergetic scope, as we've defined it here, is going to be achieved when AC is AC max. Why? Because we're arguing that standard metabolism is pretty well just a function of weight. It doesn't depend on duration. And so the only thing that's going to be likely to vary over there to make AA plus AG large is going to be a large AC. And logically, AA and AG are going to be their largest when AC is its largest. So that's the reason I would argue that bioenergetic scope will be achieved when the fish or the organism is achieving its maximum ration, maximum feeding rate, A sub C max. Now that we finally considered a specific limit, remember I told you that one of the standard approaches to trying to understand complicated problems is to try to take the problem to a limit that's natural in some sense. Because often things get simpler when you get to the limit, and it allows you to back off then and understand the general case. And in this case, I'm going to argue that, we may not know how AC varies as a function of fish weight. After all, we might have a situation where there wasn't any food around, so AC would be zero. Wouldn't matter what the weight of the animal is. If that's the case, in the long term, fish weight's going to go to zero, right? Because it's going to have to pay off the shortfall by metabolizing its already acquired biomass and energy. So it would matter in the long term, but on the short term, AC can be 0 to AC max. All those are possible. And I don't know a relationship really that relates AC itself to fish weight because of that variation. But I do know a relationship that might relate it to the maximum of that at the limit. And that is that AC max is another power function of weight with a little different exponent. Typically, minus 0.3 or so. And I use an A there to get that to an equality because the A is necessary to convert the dimensions of the term on the right to equal the dimensions of the term on the left. And the term on the left, we want to be something like calories per kilocalorie per day. So that means the dimensions of A are going to have to be calories per kilocalorie per day. But the actual magnitude of the scalar part of that is going to depend on what the dimensions are, the ancestral dimensions of weight. Are we measuring weight in grams or tons or ounces? Whatever we measure weight in is going to affect the scalar part of the quantity A. Is everybody with me on that? That's the reason I keep talking about the fact that you need to retain these ancestral dimensions. Most folks would argue that when you convert something to a power that's different from 1, you lose its dimensionality. That weight may be measured in grams, but weight to the minus 0.3 has no dimensions. It has ancestral dimensions, and there's another way of looking at it. You can go through some fancy algebra and argue that there are dimensions, but I think it's easier for most folks just to take transforms like powers that are not unity of quantities like weight, take those as dimensionless, take logarithms as dimensionless. And so that's what we're going to do. Well, that aside, whatever the dimensions of A are, they have to match up with AC max. And they're going to depend on what the ancestral dimensions of weight were. Well, not the dimensions of A, but the scalar quantity, the scalar part of A, as opposed to the dimensional part, making the whole thing a vector. And this leads to a simplified expression for bioenergetic scope for activity and growth, because now we can combine those weight terms and get it down to 6/10 of AW to the minus 0.3 minus S times weight to the minus 0.2, and that's bioenergetic scope. Is everybody with me to that point? I think what I did there was take AC and just do what? set it to AC max, and then set AC max to the relationship it has to weight. That's all I did. So now we got a difference equation. It says the scope for activity and growth, the bioenergetic scope, is the difference between basically assimilated energy and respired energy. I say it's easier to appreciate graphically, at least for me at least, and it might be for you. One thing I notice is that if I take logarithms, I convert these relations to straight lines, and there are the straight lines. And so let's graph the logarithm of the terms a sub I, whatever they are, as a function of the logarithm of weight of the fish. And let's start at the top with AC max, which is proportional to weight to the minus 0.3. If we put a constant in there and make it AC max equals weight to the minus 0.3, then we can actually put numbers on this scale over here and actually position the graph to start at the right number. But I don't want to get down to the point of actually putting numbers. I just want to look at the shapes of the relationships and the concepts. So I claim that the rate at which fish can consume food when you convert to log is a declining function of weight, and that the slope is minus 0.3, we're going to say, at least in this case. And then I'm going to go ahead and say that the waste is associated with the rate of consumption, and that will simply be 25% of whatever AC max is, and so it'll be a parallel line that has a difference here that corresponds with this 25% value. And that don't look like 25%, but remember this is a logarithm. And then A sub D is another 15% off. And so we end up with this line here, this red line that's on the bottom, being essentially the assimilated energy as a function, the maximum assimilated energy as a function of fish weight. Now coming up from the bottom, and this is the way it's usually done, you come up from the bottom with requirements and come down from the top with supplies. Coming up from the bottom is the standard metabolic rate. And that's also a declining function of fish weight, but with a little bit less steep slope typically, minus 0.2 instead of minus 0.3. Well, it may occur to you now that if that's true, if all of that said is true, then sooner or later, somewhere out here at finite values of weight, you're going to get an intersection of this assimilated energy line down here. That's the difference once we've deducted the obligatory losses for waste and food processing, and this requirement for energy that standard metabolism represents. Sooner or later, those two lines are going to intersect. It may also occur to you, if you're thinking ahead a little bit, that this represents an endpoint in terms of weight. You can't get any bigger than that. How are you going to get bigger if you don't grow? If you got no bioenergetic scope for activity or growth, well, maybe you could get away with no activity, and we're going to try that game. Well, I guess that's the words. All right, let's forget activity. Let's just stop right there and say that, the argument is that if you don't have any energy available to support activity or growth, then there's no way to get any bigger than you are. As soon as you try to get a little bigger, it takes more energy to get bigger than you get out of whatever you can eat. In other words, you need more out here on this blue line at that point than the red line is providing. And here it is in words. Some people like words better. If AC max's weight power is less than that of AS, and remember that means a bigger negative number, minus 0.3 instead of minus 0.2, if the log of AC max is more steeply sloped than is the log of AS, then the bioenergetic scope decreases with increasing weight, and at some finite value of weight must go to zero. This leads to what has been called, what I call, and what other folks have called, the hypothesis of bioenergetically determinate growth in fishes. And it is that no matter how optimum the situation, no matter how much food's available, no matter how great the thermal conditions and the air saturated or even supersaturated DO, there will be a W max beyond which the fish just can't grow, because all possible A sub C goes to meet the bioenergetic overheads, leaving nothing to support growth. An explicit estimate of W max is possible if the division of bioenergetic scope between the two components, activity and growth, can be resolved or assumed in some way. Probably the best general rule and the best middle of the road guess is that Winberg's rule applies. And Winberg's rule, remember Winberg, that name keeps coming up. Remember, he was the guy that had electivity. No, I'm sorry, that's Ivlev. Okay, Winberg. There's another Winberg rule somewhere along the way I talked about. I forget what it was. Well, anyhow, this Winberg rule, is that in nature, the activity component of metabolism for fish is about equal to the standard component. In nature, the activity component of fish is about equal to the standard component of fish metabolism. That is, the combination of AS plus A is equal to about 2 times AS. And I think we assumed that in Lab 2, in the little application at the end. Thinking back, I think that probably the other mention of a Winberg rule had to do with that rate of growth was. Does anybody remember this? It was. Well, maybe you need to go back and look at your notes there and remember it better than I do. Somewhere back in there, we talked about measuring respiration of fish in the lab and their growth in the field, and then estimating the consumption of forage under natural conditions is 1.25 times the sum of AR plus AG. I think that was the other Winberg rule we talked about. That the consumption rate of food for fish in nature on an energy basis is about 125% of the sum of their respiration and their growth rate that you would get from estimating growth in the field. And we'll talk about how to do that in a little bit. This Winberg rule is related to that one, actually. This one says that half of the routine metabolism is associated with activity and half of it's standard. A guy named Danny Weiss, an Israeli aeronautical engineer, of all things, who liked to dabble with fish as sort of a hobby, developed a theoretical basis for Winberg's rule. And what he showed was, by starting with first principles and considering things like physics of thrust and drag, is that the bioenergetic cost of swimming per unit distance in fish is minimized when they swim at a speed such that their activity costs for that swimming activity is equal to their standard metabolic rate. You know, can't claim I ever fully understood the derivation and the math, but it was good enough to sell to Nature because he published this paper in Nature. And I've got a copy of it, maybe even on the server, if you'd like to look at it. So, anyhow, the conclusion's the same. Basically, the reason that Winberg's rule seems to work, apparently, is that fish have evolved so that they swim around in nature at a speed that's about that speed that causes them to spend the same amount of energy and activity that they spend in standard metabolism. That maximizes their efficiency of moving through the habitat. And why wouldn't you want to be efficient? In order to swim the furthest per unit. And that's what Danny Weiss showed. So, if you apply Winberg's rule to what I've already said, and sort of back out the activity component and see what you got left, then what you got left is the scope, the bioenergetic scope for growth. Not just the bioenergetic scope for growth and activity, but just what's there for growth. And so what this says is that when fish have to be active and have something positive for the activity component, when they can't just go to zero on that, and I'm not sure how they could if they weren't carp in a fish culture situation in a cage where they're just stuffed, or like the fatted goose, that doesn't have any activity and just basically force fed. I'm not sure that would be that likely to result in zero A sub A, but anyhow, the idea is that your maximum possible weight then goes back to a lesser value when you deduct the obligatory activity. So all this makes sense, I think, logically. Whoops. So I think I actually go through the calculations now. Yeah, Julie?
I have a question on the graph.
All right. Julie has a question on the graph.
So are the A, W, A, are they coming the lines or the space between the lines? I don't really get the whole W.
Okay, so A sub S is everything from essentially nil A sub I, although it's hard to go zero, right, with the logarithm. So it's the difference between here and here. In other words, that's the space between the two lines. A sub A is the space between these two lines. A sub D is the space between these two lines. A sub W between these two. But then A sub C is the top line. So that's where we are there. And then the difference between these two is that scope. And it goes from largest for a little fish to nil for the biggest fish. And on a log basis, the argument is it goes down linearly if you got log. So we can calculate the amounts here. Maybe this is, the algebra is easier than the graphics maybe in terms of explicit results. So we can take this bioenergetic scope model that we just had to work with for activity and growth and subtract the amount A sub A that's equal to A sub S. And so in effect, instead of having one standard metabolism, we got two, because we're arguing that the activity component's equal to standard now. So we just multiply by 2. And so now the difference between these two terms reflects or represents the bioenergetic scope just for growth, with an assumed level of activity, such that the cost of that activity is equal to the cost for standard. We can even solve for the maximum size of fish. The argument would be that weight is going to be the maximum possible bioenergetic weight when the AG goes to 0. Can't get any bigger if you have nothing for growth. And so all we do is set that to 0. In other words, set that difference to 0. Set one term. In other words, we argue that growth will be maximized, that the value of W there will be W max when that difference is equal to 0, when there's no more scope for growth left. Remember, there's AC max over here. AG max is equal to this difference. And now we're arguing AG max is 0. So setting these two terms to be equal means that we can solve the equation in terms of ratios of the coefficients by just getting all the W max terms together. And let's see, what did I do here? I took this W max over there, and I had a minus 0.2, and I divided that into W max at minus 0.3. That gave me a W max to the minus 0.1 in the numerator. I took the 0.6A and divided it over here on this side. So there's that ratio, 0.6A divided by 2S. Why this power 10? Because this W max here is coming out to W max to the minus 0.1. And so we're going to have to raise it to the power 10 to get W max. Is that right? Let me pause and think with my local folks helping me here. I'm looking for help. Okay, we're back on the record now. My local folks, help me. And what we realized was that I'd gone through several steps here between here, and it kind of obscured the outcome a little bit. First step was I took the W max to the minus 0.2 over to this side and divided it into the W max to the minus 0.1. And when you do that, when you got the division of two exponents, you change the sign on the one in the denominator and add it to the one in the numerator, and that gives you W max to the minus 0.1. Then I divided the 0.6a over here into the 2s, but notice it's upside down. It looks like I multiplied it. So what I actually did was go ahead and do that, then raise everything to the power 10. I get a W max to the minus 1 is equal to 2s over 0.6a raised to the 10th power. So then I essentially did the inverse I took an inverse of the whole function, and so I got W max instead of W max to the minus 1. You could work out the math, folks, if you just took your time and gently went through it and applied the rules that you should have remembered from math. But trust me, the final result is this result, and it's kind of a neat result. It says that if you know these coefficients A and S, you can calculate under this bioenergetically limited growth the maximum weight of the fish that you would expect to get out of the system. And this isn't an ecological, this is a biological maximum. This is the most size you could get no matter how good things are. That's the reason I call it bioenergetically determinate growth. Most of you might have learned a different kind of determinate growth studying mammals or birds. And that kind of growth has to do with the extensions of long limb bones. After a while you mature and your epiphyseal junctions sort of harden up and you don't grow longer or taller. You may get bigger. And I'm holding my arms out to my side. In other words, you get heavier, but you don't necessarily get higher once you've matured. Well, that's the kind of determinate growth that mammals have. Fish don't seem to have that kind of determinate growth, and yet they do, in theory, have this kind, bioenergetically determinate growth. So we can solve this for ecofish. We know all this stuff for ecofish. We know all these rate coefficients. And when you do, and you put in an A of 18% per day, which is what ecofish is using, and a 2.28% per day for S, which is what ecofish uses under optimum conditions, what that gives is about 5,554 grams. I think that's a little too low. That's only about, 20 pounds? Red drum get to be 60, 70 pounds, so it's a little too low. 5,500 times 2.2 is about, what is that? Less than 20, right? But just reducing S to 2.0, suppose I made a mistake. I estimated the parameter a little off. If you just reduce the S from 2.28% per day, calories per calorie per day, that gives a W max of 20 kilos. If you keep S at 2.28 and reduce the Windberg to 1.5, so now, the red drum somehow or other is pretty efficient compared to Windberg's fish and is able to move around and do all that it needs to do and only invest half of standard metabolism in activity, so its Windberg is 1.5 instead of 2. And by the way, some of the research that we've done actually points in that direction for red drum and ponds. Then you get 98,000 kilos, and that's 217 pounds. Maybe a totoaba, that's the biggest cyanid in the world lives in the Gulf of California, although it's nearly extinct. I think they get about that big. cyanids are the family to which the red drum belongs. But red drum don't get that big. But all I'm trying to convince you of is that these numbers are not outrageous. I mean, they're all within the realm of something at least conceptually possible. Solved that for tilapia one time. I don't have that solution in here anymore, and I think we got for blue tilapia something on the order of 5 pounds, which is probably a bigger tilapia than tilapia come. So this hypothesis of bioenergetically determinate growth, which a fellow named Jim Kitchell, who was at Madison for years, and I and some other folks published in this paper in Physiological Ecology, is still more or less untested. It is logically true if and only if the weight exponent for AC max is smaller than the weight exponent for AS. And evidence is starting to mount, unfortunately, or fortunately, I guess, that the weight exponent is not a constant. When fish get big enough, that weight exponent starts to drift away from that minus 0.2. Or that the weight exponent for food consumption starts to drift away from that minus 0.3. And if the two exponents get to be the same, then what that says is the lines are parallel and things go on forever. And so you have indeterminate growth. You know, the problem is we don't know much about really big fish, or big anything. You know, they don't fit in respirometers very well, or lab tanks. So it's hard to do respirometry with 30, 40-pound broodfish, you know, red drum. If we could, maybe we'd learn something about this. So that's a neat story, though, right? You haven't heard that before, probably. Activity of fish also has important effects on the way energy is distributed. The scope for growth logically must decrease to 0 at the maximum sustainable speed. And limited experimental evidence, I claim, supports that. In other words, if you swim as fast as you can possibly go, then everything you can get is going into activity. So there isn't anything left for growth. And I would add something else you probably haven't heard before that I think we were taught by Ecofish and Ecofish's predecessor, Ecophys.fish, the research model that I gave you the manuscript or the published paper for. And that is that there seems to be an evolutionary match, and logically it would have to be that way, an evolutionary match between the rate at which fish can feed their faces with substrates, or their gut, and the rate at which they can feed themselves the oxygen that's necessary to catalyze the reaction. In other words, maximum capacity of oxygen uptake and energy substrate supply rates seem to be in the same ballpark, but if anything, there's a little bit of an edge to oxygen. Experimentally, or I'm using that word wrong, experimentally, not experimentally, but empirically, using Ecophys.fish, and feeding it feeds that have different energy densities, leads to the conclusion that the optimum feed is one that has about 2,000 calories per gram if it's digestible in the range of 0.8, 0.85. What do we feed them? We feed them feed that has 4,000 to 5,000 calories per gram. What does nature feed them? Feed that only has 1,000 calories as consumed. So what this says to me is that in nature, fish like red drum, they always, almost always can get more oxygen than they can get energy from feed. But in lab or in the aquaculture, it may well be that, they could be suffering from oxygen deficiency. In other words, they don't have enough oxygen available at air-saturated conditions to supply the necessary O2 for the O2 plus first carbohydrate yields CO2 and water and energy. Everybody does remember that one, right? O2 plus C6H12O6 yields H2O and CO2 and energy that takes low energy ADP to ATP or something, you know. So what I think's going on is that evolution said, wait a minute, oxygen is likely to be a much more acutely needed resource than substrates. You know, you can always live tomorrow on things you ate yesterday, but you can't breathe tomorrow on oxygen you breathed yesterday. Fish suffocate like people in seconds or minutes, but they starve over periods of days or weeks. And so logically, you would want to be sure that you always gave the edge to oxygen, so that you could get plenty of oxygen to process whatever substrate you manage to get your mouth around. You know, I think that's what may be going on. I don't think I knew that in '96, Ray. Okay, so here is my view, and I think it's consistent with the literature on how activity affects the allocation of the energy in food under AC max conditions. This is speed, swimming speed, U, which is a commonly used symbolic representation of velocity, in body lengths per second, or speed, not velocity. What's the difference between velocity and speed? You know, the speed is the scalar part of that, and the velocity implies that there's a direction also, so that it's a vector. But most people use the two interchangeably, but when you do experiments, energy or oxygen uptake experiments, you learn that there's a big difference, you know, when fish are having to maneuver and change their direction of swimming, you know, and accelerate and decelerate, so that velocity is not a constant, even if speed is. Well, anyhow, this is speed, body lengths per second. And what it says is that standard metabolism goes along independent of speed, that the speed component, or the activity component of metabolism, accelerates as an exponential. And I've already shown you that and told you that. That food consumption rate, maximum, is pretty much independent of speed when you're at low speeds. Now, you could argue that, you know, that this is not really going to work in nature, that there's going to be a falling off over here at near zero, because you're not going to be able to catch enough to eat if you are a predator, for example. So you got to be a little bit active in order to achieve anything like an AC max, or that your AC max is actually going to be lower because you're not as capable. And then at the other extreme, maybe when you're really swimming at flat out speeds, then, you know, you're less efficient in eating. And so there's probably a nosedive over there someplace. If all this is true, you know, regardless of what's going on in the fine details with AC max, you can logically see that scope for growth is going to be maximized at, you know, maybe it's going to be maximized between 1 and 2 body lengths a second. But this graph says it's maximized at no speed at all, and goes to zero at the maximum sustainable speed, where sustainability here is measured in terms of long-term energetically sustainable. Yeah? So Ishan asked the very good question about the correlation between speed intake and oxygen uptake. And in the case of tunas, like he said, tunas, there's a 1-to-1, or not a 1-to-1, but certainly an increasing, because you don't breathe unless you swim. The faster you swim, the more oxygen you get, but the more oxygen it takes. So I'm not sure, you know, right where that gets us to, but logically, increased swimming would lead to increased rate of oxygen uptake. Well, AC max here is an energy-based AC max. It's based on the ability to consume calories. And logically, if you're swimming really fast, you're maybe not very efficient in eating the forage. You know, you overshoot as you chase, for example. Hard to imagine that if you're a herbivorous fish, for example, or a fish that grazes, that increased speed would be good, because, you know, how are you going to eat coral polyps if you're swimming at your maximum speed, or hydrilla, or whatever it is you're eating if you're a herbivore. But if you're a predator, logically, increased speed is good up to a point. And then at some point, that's going to cost you. And probably it's true with both oxygen and substrates. Increased speed in the case of tuna is going to increase oxygen supply in the water, but it's going to increase the cost of that oxygen too for that speed. So, well, I mean, I guess what we're talking about in that case is logically what is VO2, what is the maximum rate of oxygen transported away from the gills. And my guess is, in the case of a tuna, it would increase as speed increases, but at some point it would crash. In the case of ordinary fishes that have to pump, I'm not sure that swimming fast would be a good thing for ventilating the gills. It might actually interfere with the opercular work that has to go on. So, I think these are case-by-case situations that you'd really have to dig into to know. In fact, I'm not sure. Maybe there are published literature on these different types of fish and the effect of swimming speed on oxygen uptake.
I heard that. I may be wrong, but I heard that tuna is required to swim fast because if they're swimming like slowly, like if you keep them in the like cage or something like that, it will affect their oxygen intake. So
yeah.
If you want to feed tuna, you need a cage like an island.
Right.
To make it enable to swim fast, and then that's the problem.
Okay, so Ishan is saying the truth. He's saying that tunas are obligate swimmers. They have to, and I think I've mentioned this in class, they have to swim both to irrigate the gills with water-bearing oxygen. They use ramjet ventilation. And they have to swim to stay up in the water column because they're negatively buoyant. They sink if they stop swimming. So they gain both hydrodynamic equilibrium and oxygen by swimming. Faster they swim, the more they irrigate their gills. But the faster they swim, the more oxygen they use to swim. My guess is, though, that you're right, that if you confine a tuna in a situation where it's not able to be as active as it needs to be to irrigate its gills properly with ramjet ventilation, then that would decrease oxygen uptake. And one of the ideas that we had about why tunas in captivity develop this stress syndrome that I think I mentioned in class called puffy snout, where there's this overgrowth of connective tissue in the snout region. I mean, when you look at one of these sharply pointed tunas, it's turning into a bonnet-head shark before your eyes. It's like the flesh on the side of the snout is growing out, and it finally can obscure the vision. Puffy snout is the condition, and one of the arguments is that part of that stress response is the inability to swim as fast as necessary in order to gain enough oxygen across the gills. I think I also mentioned, did I not, that we learned, thanks to Reg Gooding's imaginative work, that supersaturating the water with oxygen in hauling tanks when we were catching these tunas at sea greatly improved the success of that operation. The mortality went from way more than 50% by the time we got back to the dock to only a couple of percent if the fish were dropped into the same tanks they'd been dropped into before, but with oxygen supersaturated water. So we think what happened there is the fish didn't have to swim so fast in order to have as much oxygen uptake as they needed to pay back the oxygen debt incurred by the anxiety of being caught and the hyperactivity. So that's the generic picture that I would offer, that there's got to be more scope for growth at some lower, intermediate maybe level of sustained swimming. And notice I've made U max here somewhere between 2 and 3 body lengths per second. And of course that's going to be species dependent as well, and I think it's probably a much larger number for a tuna, maybe up to 10 body lengths per second. Maybe a very sluggish form would have a tough time achieving any scope for growth if it had to swim more than 2 body lengths a second. And again, the smaller the fish, probably the larger this U max number. Little fish can sustain faster speeds than big fish. Temperature is another factor that affects the scope, bioenergetic scope. And the rule here is that there is an optimum temperature, a temperature that maximizes scope for growth and activity, and that scope goes to zero at both extremes, both high and low temperatures. Upper and lower limits for bioenergetic scope represent, in effect, long-term ecological lethal limits. You can't live forever, or you can't live out your full lifespan if you have temperature that has reduced your bioenergetic scope for activity and growth to zero. So logically, the bioenergetic limits for temperature are narrower than the biological limits, the survival limits for short-term survival. So the picture there looks like this, and I'm pretty confident about that one. What it says is that as temperature increases, the standard metabolic rate increases exponentially. AC tends to increase to a maximum and then crash, and I may have made this crash too gradual. I might should have drawn this increasing more straight up and then dropping like a rock out here at these high values of temperature. If you just deduct the standard 25% for wastes and 15% for the food processing, then you end up with bioenergetic scope in between here. And the point I made is supported that scope is maximum at an intermediate temperature and then goes to zero at certainly an extreme high temperature. In this case, notice I didn't draw it going to zero. Why would that be? Well, that would be because I was thinking about a salmonid, which is where a lot of these data have come from. And salmonids their bioenergetic scope is just truncated at the freezing point because they still have scope left when you get down to the point where the water turns from a liquid to a solid. So it's undefined at temperatures below this point. Logically, obviously, I'm thinking about a 0 degree value here now. But if you were dealing with tropicals, then logically the low end of this would look like the high end, where scope is pinched off to zero, both low temperatures and high temperatures. Even a fish like a red drum. So you can see that even in salmonids if you restrict the ration. And these generic results are actually pictures representing some of the work that J.R. Brett, a guy named Shelbourne, did years ago with a Pacific salmon of some sort. And here's the situation on the left that you just saw in the previous slide for unlimited rations. And then on the right is the picture, on the right is the picture you get with feed limitation, where you don't provide as much feed as the fish would consume. And so the argument and the result that Brett and his colleagues found was that if you increase the limitation of some limiting factor, the degree of limitation, like food as a resource, then what happens is three things, and none of them are good. You reduce maximum scope at all temperatures. You reduce you make the extreme temperatures where scope is positive come together and converge, and logically they converge to a point at some point if you restrict rations enough. And there's also something that may be less evident here, and that is that there's actually a shift in the optimum temperature to a lower value. And you can get out your ruler, print out this graph and make measurements and prove that to yourself. Or you can just apply logic, and the logic has to be that, well, if this is anything like reasonably flat up here, and this is an accelerating function, then logically the more I compress the top function down on the bottom, which isn't changing, the more it has to shift to the left. And again, don't ever forget, take things to the limit when in doubt. Think about this question. It might even show up on an exam, probably not this one, maybe the next one. What is the optimum temperature for growth, with a set of quotes around the word growth, meaning that I'm going to accept positive and negative values. Remember, that's the only term in the energy budget that can go negative. What's the optimum temperature for growth in the absence of food? If the fish is starving, what's the optimum temperature for growth? There's a reduction in the optimum as the restriction becomes progressively more severe. So what's the optimum temperature if the restriction is the maximum degree it can be, which is 0? Everybody's sitting there thinking about it. Tell me the answer. Don't doubt. You're confident. Be confident. More cold, absolutely. How cold? That's the question I'm getting at here. How about if you're a salmonid or a centrarchid, how about 0 degrees centigrade be optimum for growth? Why would I say that? Because if you are at the lowest temperature you can survive, then that's where your rate of expenditure to support standard metabolism is minimum. And so you lose weight at the slowest rate when you are numbed down as cold as you can get. So logically, I would say 0 degrees is the optimum temperature for growth for a salmonid that's starving. And I would be sure I understood I was going to allow negative values of growth. So here is what Ecofish does with DO as a limiting factor. DO and energy substrates are sort of complements. And so I did some experiments with Ecofish, or maybe this is with Ecofish's predecessor, and it probably is, Ecofizz.fish, the one that's published. And what we're showing here is growth over a fixed interval of time, and I think it's probably 7 weeks or 8 weeks, from an initial size that is indicated by the 1 line. So that would be probably about 6 grams. I think I'm looking at, this is sort of based on some experiments that one of my former students did. And so the red line there shows the final weights simulated under conditions of no limitation, that is air-saturated DO. And then the other lines show progressively lower saturation values. And the numbers actually correspond to the parts per million, DO. So it's like you did experiments. And in the top experiment, you let the water be air saturated with DO. Then you did a whole series of experiments where you had DO at 4 milligrams per liter across, you managed somehow to get 4 milligrams, even though that's going to be less saturated at high temperature than low. 3 milligrams is the brown, and the black is 2 milligrams. So you can clearly see there the optimum shifting from something up around 28.5 at air saturated to something that's down here probably closer to 25 or closer to 25 than to 28.5, something around 26 when DO is only 2. So, limiting factors, in this case DO, in the other cases energy and feed, substrates. So here's a summary statement that says the 3 bad things that happen, or not bad necessarily, but 3 things that, 3 logical results of limitation. Bioenergetic scope for activity and growth is reduced at every temperature. The bioenergetic scope is positive over a narrower range of temperature. And the optimum temperature the temperature at which scope is maximum decreases. I've made the point from the beginning that growth is a bioenergetic resultant. That is, I don't believe that there are direct effects of things like temperature and energy substrate density and DO on growth per se. I think what happens is there are effects that are more fundamental of these variables on the bioenergetics and the components, and then what happens is the growth pays the price or gains the benefit, whichever is the case. If you ask a typical fishery biologist about fish growth versus temperature, the answer you'd get back would almost always be, well, when temperature increases, first the growth rate increases to some maximum value at an optimum temperature, and then it falls. And that would be the right answer most of the time, but it depends on the context. And I actually had some experience in a situation where that was brought home in a forcible way. It had to do with growth rates of fingerling largemouth bass that were fed fathead minnows at 2% of body weight per day, fixed value, in raceways flowing at 1 body length per second. San Marcos, across the road at the Federal Hatchery, the old Federal Hatchery there, looking at Ray. And, here's the result. And the optimum temperature for growth turned out not to be at the intermediate value of temperature. Now, admittedly, the low temperature here is not 0 degrees. But it's relatively low. And so the picture you get is, well, standard metabolic rate is increasing as a function of temperature. It's accelerating. But everything else is fixed. They're being fed at 2% of body weight per day. And you take off the deductions that are fixed then as proportions of that. They're swimming at 1 body length per second, so even A sub A is fixed in this case. And so what you're left with is a scope for growth. And the picture you come out with is that the scope for growth is the lowest temperature tested at maximum. That maximizes the scope for growth. So they grew faster at the lowest temperature. And as temperature went up over the range of the experiment, growth went down and down and down, and there's the pattern. So a bioenergetic analysis is consistent with the observed result. And a little different from what intuition would have said if somebody just asked you out of the blue. Okay, so we're done with that set of material. The next session after the exam will be sort of the wrap-up, and it'll focus on growth models, empirical growth models that are applied in fisheries and aquaculture, and the convergence of empirical growth models with bioenergetics, sort of completing the picture. So we'll stop here for today and wish everybody successful studies for the exam. I'm open to questions if you've got any about the material. I would like to answer any questions on the record for the entire group, so I think the easiest way to handle that would be for you to email me your questions, and then I would email any response to everybody in the class. That would be fairest, I think, to everyone. The other possibility, though, that I'm open to is we have, today's a Tuesday, it would be a help session day for Lab 3. Everything is up, by the way, on the server for Lab 3. You can complete all the work, but as I said in my email when I notified you about that last night, my recommendation is that you delay your real focus on Lab 3 until you take care of the exam, even though that's going to give you an extra day or so to catch up. If it were me, that's what I would do. I would invest my effort now in getting ready for that exam, and probably take this afternoon to do that if I needed to, instead of spending it on lab and then catch up this weekend with lab. The lab report won't be due till a week from today. But that being said, I would be prepared to meet with all of you or a subset of you or people who are not here that, well, I guess I probably won't get the word to those people, will I, before lab? Because even though I run up and post this, it'll still probably not get to people. But if anybody here would like to get together, we could do a live session with recorded questions and answers. Actually, I would prefer to do it by email because I think that'd give you more time to think. You may not be at the point in your studies that would really give you a good return on that investment anyhow. So unless somebody has a strong desire, I'm going to suggest we pass on that suggestion and that you just email me any questions. Or, if you want to, call me and I'll try to rephrase the question in an email that I send out to people and answer it if I have an answer. I may not have an answer to your question. A lot of questions I don't know the answers to, but I'm going to try to know the ones that I ask you. Okay, we're going to stop here then.